Good morning. Today I'll see about asynchronous sequential circuit design. So already we have seen one problem. This is one more problem for this asynchronous sequential circuit design. Now listen. Design an asynchronous sequential circuit that has two inputs, x1 and x2. So the two inputs are x1 and x2. And one output is z. So z is one output. The output z is equal to 1 if x1 changes from 0 to 1. If x1 changes from 0 to 1, then the output z is equal to 1. Similarly, if x2 changes from 0 to 1, z is equal to 0. So if x2 changes from 0 to 1, the output z is equal to 0. And z is equal to 0 otherwise. So otherwise z will be equal to 0. Now realize the circuit using SR flip-flop. So we must use SR flip-flop. Now listen, this is the condition. That is, if x1 changes from 0 to 1. Now let us take initially the present state is A and the inputs x1, x2 are 0, 0. Now the output initially z is equal to 0 because here we don't have any changes. So present state A, input x1, x2, that is input x1, x2, 0, 0. Output z is 0. First time here we have 0, 0. So if we have only one bit change, the 0, 0 will become either 0, 1 or 1, 0. Here we have 0, 0. If we have single bit change in the 0, 0, we will get either 0, 1 or 1, 0. So that is what we have written here, 0, 1 or 1, 0. So this 0, 1 is x1, x2. Here it is x1, x2. Now here x2 changed from 0 to 1. So if x2 changes from 0 to 1, output will be 0. So output is 0. Similarly, if x1 changes from 0 to 1, if x1 changes from 0 to 1, initially we had x1 as 0, now it has been changed to 1. Now the output will be z is equal to 1. Now this is a new states, so we are giving this name as B, C. Now the present states are B and C. Now what will be the next state of this B? Now let us see here. Here we have 0, 1. So if we have 0, 1 and if we have one bit change, either this will change as 0, 0 or we can change this as 1, 1. I hope you understand. We have 0, 1 here. So we have 0, 1. If we have single bit change, either we can change this 1 as 0 so that this will be 0, 0, or we can change this 0 as 1 so that the next state will be 1, 1. So that is what we have written here, 0, 0, 1, 1. Now check here, x1 changes from 0 to 1. If x1 changes from 0 to 1, z will be equal to 1. So z will be equal to 1. Next, if we don't have any changes, that is here we don't have any changes. Here x2 changed from 1 to 0, but here we don't have that 1 to 0 changes. We have only condition is from 0 to 1, 0 to 1, but here 1 to 0. This x2 changed from 1 to 0. So otherwise z is equal to 0. So we must use this otherwise z is equal to 0. Therefore 0, 0, 0. Already the state is existing A. 0, 0, 0. So 0, 0, 0. So we have to represent the same state A. But here we have 1, 1 slash 1. That is x1, x2 inputs 1, 1. Output is 1. So this does not exist previously. This 1, 1 by 1 condition does not exist previously. So that we can give another new name D. That is now our present state is D. Since this is existing already, so we have to stop here. Now here we have C as 1, 0. So if this 1, 0 is changed, if we have only one bit change, either this will be changed as 1, 1 or this will be changed as 0, 0. So this 1, 0 either we will get as 1, 1 or we will get as 0, 0. If we have single bit change in this 1, 0, so it will be changed as 1, 1 or it will be changed to 0, 0. Now listen here, x2 changes from 0 to 1. If x2 changes from 0 to 1, z will be equal to 0. So z will be equal to 0. Here we don't have any changes because 1 to 0, we don't have any condition like 1 to 0. So the output remains 0. And this exists already. So A, this state exists already, so we are giving the same name A. But here 1 1 by 0, up to this we don't have that condition. This state does not exist previously, so we are writing this as E, because A, B, C, D already we have written, so we are writing here E. Now let us continue here. So here we have 1 1 by 1. Now 1 1, we have 1 1. So if we have single bit change in this 1 1, either this will be changed as 0 1 or this will be changed as 1 0. Either this one changes to 0 or this one changes to 0. So that we have 0 1 1 0. Now check here, 1 remains 1, but here x2 changes from 1 to 0. So here we don't have 1 to 0 condition. So otherwise, that is, output will be 0. And here we have changes from 1 to 0. x1 changes from 1 to 0, and here we have 1. So the same thing 1 here. So otherwise 0. So we have 0. Now check here, the 0 1 by 0, this exists already. So here we are giving name as B. But this 1 0 by 0, this is a new condition. We don't have previously like this. So we are giving new name F, that is A, B, C, D, E, F. Now let us continue here. Here we have 1 1 0. So the same thing, 1 1 0. So if it is 1 1, if we have single bit change in this, either this one we can change as 0 or either this one we can change as 0. So here we have 0 1 or 1 0. So here we have 1 is changed to 0. So we don't have any condition like this, and this one remains 1. So otherwise 0. So output will be 0. The same way, here we have 1 1 and this 1 changes to 0. If 1 changes to 0, we don't have such condition. So otherwise z is equal to 0 exists. And now check here whether we have this existing, this states are present in the existing states. So here we have 0 1 by 0, so this is B. And here we have 1 0 by 0, and this will be F. Now no need to continue this too, because this is existing state. So let us stop here. And here we have a new state, that is F. Now continue here. If this is 1 0, present state is 1 0. So we can change as 1 1 or 0 0. So if we have only one bit change, we can change this 1 0 as 1 1 or 0 0. So 1 1 or 0 0. Now see here, 1 remains same, but here 0 changes to 1. x2 0 changes to 1. If x2 0 changes to 1, the z will be 0. Next, here A, that is 1 changes to 0. We don't have such condition, and 0 remains 0. So the output will be 0. Again, if you continue here, what happens? This 1 1 will become 0 0 1 1 0. So that will be our existing condition. So that we have to stop here. That's it. Now we have to draw the state diagram for this diagram. Listen here. This is our present state A. Present state A remains in the same state when it is 0 0 and the output is 0. So this is the present state and this represents output. And if it is 0 0, it remains in the same state. Next, A goes to B and C. When it will move to B and C, A present state, and next state will be B and C. When it is B and C, when it is 0 1. So when it is 0 1, it will move to B. When it is when it is 1 0, it will move to C. So A, when it is 0 1, it will move to B. A, when it is 1 0, it will go to C. So A 0 1 B, then A 1 0, it will move to C. Now what is the output for B? That is 0. What is the output for C? That is 1. Where is C? So that is 1. Next, B, if B is the present state, the next state for this is D and A. So for B, D and A are next states. So when it will move to D? When it is 1 1. So when it is 1 1, this will move to D and the output is 1. So and the output is 1. Next, B will move to A. B will move to A when it is 0 0. So 0 0 and the output is 0. Next, here we have D. Here we have D. D will move to F and B. So D will move to F, see here, F and B. So F and B. So this is when it is 0 1 and here it is when it is 1 0. Next, F will move to E and A. F present state, it will move to E and A. So here we have E and here we have A. So we have to check this arrow marks, and this 1 1 represents states, and the slash numbers we have written, this represents the output state. Next, C. C will move to E and A. Now C will move to E and A. So here we have C and this will move to E and A. So here we have E and here we have A. So C move to E and C will move to A. So here it is A. So that's it. Then we have E that will move to B and F. So E will move to B and F. So when it is 0 1 it will move to B. When it is F 1 0 it will move to F. And here this conditions represents. So listen here. B, here we have 0 1. So B will remain in the same state 0 1 and C will remain in the same state when it is 1 0. C will remain in the same state when it is 1 0. Then D remains in the same state when it is 1 1. D remains in the same state when it is 1 1. F remains in the same state when it is 1 0. So F remains in the same state when it is 1 0. Then E remains in the same state when it is 1 1. So E remains in the same state when it is 1 1. So this is how we have to draw the state diagram. So after the state diagram, what we have to do is we have to write the primitive flow table. This is our primitive flow table. So what will be there in the primitive flow table? That is present state, next state, output. So present state, what are the present states present here? A, B, C, D, E, F. So here we have A, B, C, D, E, F. And what are the next state and outputs? Here the next state represents our input, that is x1 and x2 when it is 0, 0, 0, 1, 1, 1, 1, 0. And the output is Z. So here we have mentioned the output. So that is what we are going to represent in the table form. And A, now check here, A, when it is 0, 0, it remains in the same state. A, when it is 0, 0, it remains in the same state and the output for this is 0. A, when it is 0, 1, it moves to B. A, when it is 0, 1, it moves to B. And here listen, if the present state is A, then we must get only A. Then only we have to write the outputs. If we get some other state instead of this A, then we should not represent output. We must represent as dash. That is what we did here. Then A, when it is 1, 1. So this condition does not exist. So that we are mentioning this as dash dash. Then A, when it is 1, 0. So check here. A, when it is 1, 0, it goes to C. So A, when it is 1, 0, it moves to C. And the output for this is 1. But you should not mention output because this is for the present state A. This is said to be primitive flow table. And in the similar way, we have to write for B, C, D, E, F. Now check here. B, when it is 0, 1, remains in the same state. B, when it is 0, 1, it remains in the same state. So we are writing the output, that is 0. Okay. If B is 0, 0. So check here. If B is 0, 0, it goes to A. So if B is 0, 0, that goes to A. Then if B is 1, 1, that will move to D. If B is 1, 1, that will move to D. Next, if B is 1, 0, so that condition does not exist here. So that we have mentioned that as dash dash. So in the similar way, we have to fill this primitive flow table for A, B, C, D, E, F. And here the output should be written only for that particular present states. So the output for A should be written. And here if you get B, then it has to be written. And here if you get C, it has to be written. And the states which does not exist should be represented as dash dash. So here D will never have 0, 0 state. So that we are representing as dash dash. And here for E, we are getting output 0 here. So for F, we are getting F here. So that is the reason why we used to circle this. So where we are getting the same states, we have to circle that. Then the next, we have to reduce the primitive flow table. Now check here, this is said to be primitive flow table. So we can reduce this primitive flow table. How can we reduce the primitive flow table? By merging this. Now let us check where we are getting same. So see here, this A and C will be in the same because here we have AA 0. So here we have dash. Okay, it doesn't matter. B and we have dash. And here we have dash dash. So here we have E. So we can fill this dash in anything. We can fill anything. So that we can take this E here. Next here we have C, C. So this dash, we can take the dash as 1. So we can combine this A and C. The same way we can combine B and D. Now check this B and D. So here we have BD, here we have A dash. So here we have A dash. And here we have B comma 0. And here we have B comma dash. Here we have D comma dash. Here we have D comma 1. And dash dash. Here we have F comma dash. So that is B and D. And finally we are going to merge this two, E and F. So in this dash we can take this dash as A. So dash dash B dash dash E 0 F 0. So we can combine this AC BD EF. So after combining we can give a name for this, that is S0, S1, S2. And here we have, this is called as merger graph. So first what we have to do is A, B, C, D, E, F. Now what are the present states we have merged? This is A, B, C, D, E, F. So we have merged this A and C. So A and C. Next we have merged B and D. So B and D. Next we have merged E and F. So that's it. This is called as merger graph. Now we have to represent this by using a states. That is, this A and C is said to be S0. B and D is said to be S1. E and F is said to be S2. So S0, S1, S2. This S0. Now check here this two. Here we have A. So A means that is S0. So we have to represent S0. So if we get S0, S0, then we have to represent output. If not, we should not mention the output. Then next one, here we have B. So where we are getting B? S1. So we have to represent that S1. Next here we are getting E. So where we are having E? So we are using S2 for E. So substitute S2 here. Then here we have C. So we have merged this A and C, that is S0. S0 comma 1. Because this is S0 state. Wherever you are getting S0, then we have to represent the outputs here. Similarly S1, S2. So what are S1 and S2? That is B and D. Now check this B and D. Here we have A. So A is S0. S0. Then here we have B. So B is S1. So S1, since it is S1 state, we have to represent this output. Then here we have E. So E is S2. So we have to represent S2. Here we have D. D. So D is S1. So this is S1. Next here we have dash, that is F. So here we have S2. So S2 comma dash. We are getting S1 here, that is for 0, 1 and 1, 1. So we have to represent the outputs here. Then S2. Now let us move on to the S2, E and F. Check here, here we have A, that is S0. B, S1, because B is S1. Here E. So E is S2. Next F. F is S2. Since it is S2 here, we have to write only the output for this S2. So we have written the outputs. Now circle the states where we are getting the same present state. So for the next state, if we get the same present state, circle the state S0, S0, S0. S1, 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 S2, S2, S2. Then the next, what we have to do is, we have to assign the binary values based on race-free state assignment. So what we have to do is, we have to assign binary values based on this race-free assignment. So let us substitute S0 0 0, S1 0 1, S2 1 0. So previously we have written this S0 S1, isn't it? So for that, what we are going to do is, we are going to assign the values for that. So we are going to assign values for this table. Now for this reduced primitive flow table, we are going to assign the values. Now check here. This is S0. Here we have S0, isn't it? S0, S1, S2, 0 0 0 1 1 0. Now here we have S0 0 0. Here we have S0 S0 0 0 0 0, and here we don't have output dash dash. Next here it is S1 0 1 0 1 0 1, and here we have output 0. So the remaining will be dash. Here we have S2. S2 is 1 0. For S2 we have to substitute 1 0. So S2 is 1 0. Here we have S1 0 1, S2 1 0, and here we have 1 0 outputs. Just compare this with the previous table with this table. Now here we have S0 S2 S2. S0 0 0. This is 1 0 1 0. So 1 0 1 0, and here we have output 0. So this is how we have to assign the binary values. Now what is this race-free assignment? Why it is called as race free assignment? Listen here, the present state and next state should be adjacent, but here the present state and next state are not adjacent. So if it is not adjacent, race condition will occur from the circuit. How we are saying that the race condition will occur? Now listen here. Here the present state is 0, 0. The next state we must have only one bit change. See here 0, 0, 0, 0, 0, 1. So only one bit has changed. Similarly 0, 1, 1, 0, 0, 0, 0, 0. Now check this 0, 1, 0, 0, 0, 1, 0, 1, 1, 0. Here 2 bits are changed. 2 bits are changed. So if we get changes like this, then the race condition will occur. So that what we have to do is we have to state the assignments, that is we have to assign the binary values according to the race free state assignment. Now check this, this is 1 0 0 0, but here we have race condition, that is 0 1. 2 bits are changed, so we should not get 2 bit changes. If you get 2 bit changes, then we will get the race condition. So what we have to do is we have to change this, and here check this 1 0 1 0 1 0 1 0. So we are getting race here and here. So for that what we have to do is we have to add one more states here. So this is here we have added one more state, that is 1 1. So where we are getting that race condition, only there we have to write the values. See here 1 1, here we don't have any race condition, so that we have mentioned dash dash dash, and here we are getting race condition. So what we can do is here we have 1 1. Let us assume that here we have 1 1. Now we have changed this 1 1 here and we have taken that 0 1. So here we have 0 1. So we are exchanging the values. We are going to take this 0 1 to the 1 1 next state, and we are going to take this 0 1 to the 1 0 state. Now let us check here. Now we have only one bit change. So we don't get race condition here. Now the same way here we had 1 0 previously, but what we did is we have added a new state 1 1, and here we have 1 1. So we have exchanged this 1 1 with this 1 0. Now this 1 1 will move here and this 1 0 will come down, so that here we don't have race condition. So this table is said to be race free state assignment table, that is for every present state, in the next state we must have only one bit change, but previously we had 2 bit changes in these 2 places. Now for this purpose what we did is we have added another new state, that is 1 1. So after adding this 1 1, we have exchanged this 1 1 value with this race condition. Now what happens? See here also we have only 1 bit change, and here also we have only 1 bit change, and this table is said to be race free state assignment table. Now let us move on to the next, and in the problem they have mentioned that we must use this SR flip-flop, isn't it? They have mentioned us to use SR flip-flop. This is the excitation table of SR flip-flop, that is present state, next state, and your SR 0 0 0x, 0 1 1 0, 1 0 0 1, 1 1 is x0. Now what we have to do is, now let us take this race free state assignment table. Now we have to compare this race free table. 0 0, present state 0, next state 0. If our present state is 0, next state is 0, what is SR? SR is 0x. So this is actually SARA, this is for SBRB. So we are going to use 2 flip-flops. One is A flip-flop, another one is B flip-flop, because we have only 2 inputs, x1, x2. So here we have only 2 flip-flops. This is SR flip-flop 1, this is SR flip-flop 2. What we have to do is we have to compare 0 0. Now check this 0 0 excitation table for SR 0x. Next here we have 0 0. So here we have 0x. So like this we have to compare these values. And now what is 0 0? Here we have 0x. For 0 1, it is 1 0. For 0 1 it is 1 0. Same way for 0 1 it is 1 0. I hope it is visible. Okay. For 0 0 it is 0x. Next for 0 0 0x, for 0 0 0x. So what we are doing is for this race pre-assignment table, we have to compare this A, that is present state, next state A plus value, because this is A plus B plus. So this is A plus B plus. So compare this 0 0 0 0 and check this 0 0 value in SR flip-flop. Now what is 0 0? Here we have 0x. For 1 0, it is 0 1. For 1 0 it is 0 1. Next for 0 0, that is 0x. For 1 1 it is x0. For 1 1 it is x0. So like this we have to complete this table. Hope you understand. See, this is race pre state assignment table. This is our present state. This is our next state. Now this is A plus, B plus. So compare this 0 0 and check here what is the value. We have to fill this table. Similarly for 0 0, next 0 0 1 0 1 0 0 0. Here we don't have anything, so we have to represent dash only. Next 0 0 for 0 1, for 0 0, for 1 1, for 1 1 0 1 1 0 1 1. Next 0 1 0 0 0 0 1 1 1 1 0 0, and here we don't have anything. And here again 0 0 0 0 0 1 1 1 1 1 0 0 1 1 1 0. So compare like this, and we have to write this flip-flop inputs from this SR table. So compare this and fill this table. So after filling this table, what we have to do is, this is for SA, this is for RA, this is SB, and this is RB. So we have to draw the K-map for this. See here, this is SA, isn't it? This is for SA. K-map. Check here for 0 0, AB 0 0. Here we have AB, here x1 x2. So here we have AB and here we have x1 x2. Now we have to check only this A values. When AB is 0 0, x1 x2 are 0 0, then the input is 0. So see here 0 0 0 0 1 0. So 0 0 1 0. Next 0 0 0 1 0 0 0 1. Next here we have 1 1. This you have to check this correctly. Here we have 1 1, here we have 1 0, but in the table we have written 1 0 1 1. Now we have to check for 1 1. So if it is dash, we have to represent the dash as 0. So 0 0 0 x 0 0 0 x, because here it is 1 1 1 0, but here we have mentioned this 1 0 1 1, so you should not get confusion in this. So this is SA. Now RA. How can we fill this RA? So listen here. How can we fill this RA? This is RA. So X. So here it is X 0 X 0 X. Next X then X 0 X 0. Then this is for 1 1 0 1 0 0 0 1 0 0. This is for 1 1. Then for 1 0, we have to check here for 1 0 1 0 0 0 1 1 0 0 0. So like this we have to fill this SA RA SB RB. So now let us check for SB, that is 0 1 0 0 0 1 0 0. Next for 0 1, that is 0 x 0 x. Next for 1 1, here it is 0 x 0 0 0 x 0 0. Then for 1 0, now for 1 0, that is 0 1 0 0 0 1 0 0. Next RB. So this is our RB. So we have to take this RB. Then we have to take this Z value. So that's it. We have to fill this K-map and we have to find the answer. And we I've said about this K-map many times, so no need to explain this. So if you pair this, you'll get BX1 X2 bar, and if you pair this two, we'll get B bar. Check here, these two 0 1 cancel, so here we have B bar and here it is X1 X2. Similarly, we have to pair this two, and this is one pair, and this 4, group this 4 and group this two write the answer for this. And here we cannot pair this because this one is left alone and this one is left alone. So write the answers for this. And final step is we have to write the expressions for this. Now what is SA? So from this we can write SA is equal to B1 bar x1 x2 plus BX1 x2 bar. What is RA? BX1 bar x2 plus B bar x1 bar x2. What is SB? SB x1 x2. What is RB? So from this we are going to write this SA, RA, SB, RB, Z. And last step is what we have to do is we have to draw the logic diagram for this. So already I said about this in the previous problem. So this is our x, x1, x2, x2 bar, A bar, B bar. Now we have to check this. Yes, A is equal to B bar x1, x2. So B bar x1, x2. So we have taken this line B bar x1, x2. Then B x1. So B x1, x2 bar. So we have added this because these two are in the addition. So add this 2 and give this to SA. Then first we have to draw the two flip-flops SA, RA, SB, RB. Now we have to give this connection. That is what is RA. So RA is B x1 bar x2 plus B bar x1 bar x2 bar. Since I don't have place, I left this. We have to add this here. So the similarly, what is SB, RB? Finally we have to draw for Z. So this is how we have to complete this asynchronous problem. So first step is you have to draw the state diagram, then primitive flow table, then reduce the primitive flow table, then check for the then assign the values for that, then check for race free state assignment, then go for the K-map flip-flop inputs. If they have given the flip-flop excitation, if they are asking to use any flip-flop, then you have to use the flip-flop. If not, you can leave the problem. And the last step, or if they are giving in the question use this SR, JK, T, D flip-flop, then you must use that flip-flops. So finally use a K-map, reduce the expression, then draw the logic diagram. Hope you understand. Let us meet in the next video. Thank you.